My name is Ashley. I am currently a third year double majoring in mechanical engineering as well as human biology. My project is more or less in the mechanical engineering field. It is on fiber Bragg grating signals. So basically, what it is it's incorporating sensors into a material to be used on a surface such as the hull of a ship, and it allows for us to actively see where damage is done to the material, so that way it is a lot easier to identify the source and fix what is wrong. I'm around just over halfway there. So far this is what I have. So basically the background behind my project is structural health monitoring. So if you're familiar with like biology concepts and things of the like, structural health monitoring can be thought of as more or less an inorganic peripheral nervous system. So basically what it does is it takes, there's things that initiate contact with it, and then we can see damage through that contact. So what happens for my lab is we are doing the basic research to understand how FPGs transmit strain waves and stress waves through aluminum plates. So there's 5 main parts to this. So the first part of this is we simply just break a pencil. So what happens is we push the pencil down, so like that, and then what happens is it applies a pressure, and once it breaks like that, the pressure is instantaneously released, and that causes stress and strain waves to propagate throughout the material. So the pencil breaking was step 1, and now step 2 is the waves propagating through the material. And since there's an adhesive right here, what that allows it to do is when it goes into the actual fiber optic cable, it goes into compression and tension, which changes the fiber Bragg wavelength. So it refracts a different wavelength. And that can be seen right here. So right here is just the traditional unaltered FPG. So that would induce the regular fiber Bragg wavelength. And then here's one in tension. So basically when a fiber Bragg is in tension, it can be thought of as being pulled on both sides, so it stretches out. And then when the fiber Bragg wavelength is in compression, it can be thought of as being pushed. So it's more or less, they're closer together. As far as the most familiar application, it's a very relatively new, and it's used in mostly naval as well as buildings. So the general public may or may not be aware of the applications, but the most long-term that has been identified is with concrete, simply because it is the easiest to embed a sensor into concrete as compared to metals. Yes, so they can be used in submarines as well as the hull of a ship. So what would happen is the actual fiber optic cables are threaded into the metal, and that allows for us to see where exactly the damage has occurred or where exactly the vessel has been hit. To further explain the concept, I kind of like to parallel it with the more or less the peripheral nervous system. So your body has dendrites to tell it exactly where something is either touching you or where something has gotten cut or something of the like. So we're basically trying to implement that concept into the exoskeleton of a ship. And so what I have added since last time is parts 4 and 5. So for parts 4 and 5, basically the signal is produced. So when the signal is produced, what happens before it is produced is the fiber Bragg wavelength is refracted, so it's sent back that way. And that happens due to a difference in the spacing between the FPGs. And then, yeah. So, and then these are like the waveforms produced, and this is just the raw data. This has not been put through a noise filter or anything of the like. And we can see that for the 0 degrees, it has a higher amplitude at the point of initiation, and that goes down as the angle gets further and further away from the actual position of the fiber optic cable. And it's something that's very important to note with this research is that fiber optic cables are very, very sensitive to any sort of noise. So before time equals 0, that shows the background noise, and that we use the amplitude of that to help gauge the amplitude of the peak wave. So basically, if this amplitude is higher, then we can't necessarily say that the amplitude at the point of initiation for 0 degrees is higher than the point at 45 degrees. But since the amplitude of them are around the same for all of them, then we can say that, hey, this amplitude is higher than that amplitude. And that is my research in a nutshell.